Today we start with the new topic, that is linear quadratic Gaussian control. In this chapter we present the important design technique of linear quadratic Gaussian control. While designing this method, we have to minimize the expectation of the weighted sum of the regression error and the control effort. This is the correct method to design any controller as compared to the approximate approach which is used to design the generalized minimum variance control. To design the LQG control, the technique which is used, it is similar as to design a minimum variance control for non-minimum phase system. Non-minimum phase system is a system for which there are some zero. The system contains some zero in the right hand side of the S-plane. The LQG controller is considered as a standard control to compare the performance of other controller. The reason why this LQG controller is considered as a standard controller, because when the control weight is reduced to 0, that is u of n is, when we keep u of n is equals to 0, the performance of the LQG controller becomes same as that of the minimum variance controller while satisfying the closed loop stability. But on the other hand, the closed loop system with the generalized minimum variance control and the GPC becomes unstable for non-minimum phase system when we put control efforts is equals to 0. This is the basic difference between the LQG control and the GMVC and GPC control. There are many methods to design the LQG control. We will see step by step. The first approach to design the LQG control is a spectral factorization. In spectral factorization, we can split the given polynomials into two factors, one with all zero inside the unit circle and other with all zero outside the unit circle. We start our discussion by explaining the concept of self-reciprocal polynomial. To understand this concept, let us consider a polynomial in the form of Z inverse. Let us consider a polynomial A in the form of Z inverse. The structure of this polynomial is a0 plus a1 into z raised to minus n plus up to an into z raised to minus n. N is the degree of polynomial A, and for this polynomial with the reverse coefficient we write another polynomial that is AR with the reverse coefficient. The structure of this polynomial is a0 into z raised to minus n plus a1 into z raised to minus n plus 1 plus up to an. How we write this reverse polynomial? Let us consider here. We just write this polynomial as it is here, but here we add one term, that is this term. The last term is an into z raised to minus n. The term previous to this is n. The term previous to this is a of n minus 1. At the same time, z raised to minus n plus 1. For this a polynomial, we have write this AR, that is this is with the reverse coefficient. Now let's suppose that we have assumed the reference. We have first assumed this a polynomials only. For this a polynomial, suppose we have assumed up at this instant this is instant as a reference. Now if we assume this as a reference, we have just we have to replace the value of z raised to minus n only, as we assume the reference as it is here. This is the coefficient of an into z raised to minus n. We have to replace this value, the place of z raised to minus n from this value to this value. Means we have to replace this place of z raised to minus n from this instant to this instant. Means it becomes the powers of a0. Means once we place this z raised to minus n from this instant to this instant, it becomes as a0 into z raised to minus n. Likewise, we have to replace the place of this z into this. Means this z inverse going in this place, and this z raised to minus n plus 1 is going in this place. In the same way, the this becomes as a1 into z raised to minus n plus 1. At the same time, it also becomes a2 into z raised to minus n plus 2. Likewise, as we transfer this coefficient from this instant to this instant, this coefficient are also transfer from this instant to this instant. Therefore it becomes set as a of n minus 1 z raised to minus n, and this here a0 into z raised to 0, therefore it becomes as only an. From these two polynomial you can understand how we write this reverse polynomial. Now we can derive the relationship between ar of z raised to minus 1 and a of z in the power of z. We can write the equation 13.2, that is previous equation, this equation. From this equation we have take z raised to minus n common, and by taking this z raised to minus n common, the equation becomes ar of z raised to minus 1 is equals to z raised to minus n into bracket a of 0 plus a1 into z raised to 1 plus up to an into z raised to n. And from this equation we can write the conclusion that ar of z raised to minus 1 is equals to z raised to minus n into a of z. This a of z is written from the analysis from a of z raised to minus 1. Instead of z we have put here z raised to minus 1, then it becomes a of z raised to minus 1. Therefore we have taken here a of z. Now a polynomial zeta of z raised to minus 1 is self-reciprocal if it satisfies the following property. The property is zeta of z raised to minus 1 is equals to zeta with reverse coefficient into z raised to minus 1. If this property is satisfied by our polynomial, then we can say that the polynomials which we have taken is a self-reciprocal. But we here calculated that our a of r into z raised to minus 1 is not equals to a of z raised to minus 1 previously. From these two polynomials we can't conclude that this a of z raised to minus 1 is equals to ar of z raised to minus 1. That means this property of self-reciprocal is not satisfied by polynomial a. Therefore we go for next solution. As the previous property is not satisfied by polynomial a, therefore we go for second approach. The second approach is we have to multiply this a polynomial with the reverse polynomial, and we have to multiply these two brackets. This bracket is for this polynomial for a of z raised to minus 1, and this bracket is for ar of z raised to minus 1. This a and az, ar were taken previously. We have taken this two polynomial as it is. Here we have taken the just multiplication of a polynomial and the ar polynomial, which is polynomial with reverse coefficient. This polynomial is same as this polynomial. Here we have just write only simplified term in this polynomial. You can see here when comparing the coefficient for different z power of z, first we have to compare the powers of z raised to 0. For this we have to multiply this bracket to this column. For the power of z raised to 0, we have to multiply this a0. When we multiply this a0 with the an, then we get the power of z0. Means when these two terms are multiplied, the coefficient for this is z raised to 0. Therefore z raised to 0 is equals to a0 into an. Likewise we have to also collect the term for z raised to minus 1, that is coefficient of z raised to minus 1. For this, when we multiplied this a into z raised to minus 1 with an, it becomes as a1 an into z raised to minus 1. And the other term for the z raised to minus 1 is that once we have multiplied this a0 for this term a of n minus 1 into z raised to minus 1, it also comes as a of n minus 1 into a0 into z raised to minus 1. Means this is the also coefficient for z raised to minus 1. Therefore the coefficient for the z raised to minus term are, first one is this a1 into an, and the second one is this a0 into a of n minus 1. From this comparison, we can calculate the coefficient of z raised to 0 and z raised to 1. Here the previous terms are written as it is here. There is no difference. That is powers of z raised to minus 1 as first we have taken z raised to 0, and the second is z raised to minus 1. This is the same term as it is previously. I write these previously terms for your understanding purpose only. Likewise, we compare all the coefficient of z. Now we change the order of multiplication. Previously, here you can see first we take a of z raised to minus 1, and then we take ar of z raised to minus 1. But here we have taken first the reverse polynomial, that is ar, and then we take a. With this multiplication, the first bracket comes for reverse polynomial and the second bracket comes for a polynomial. Here we take the simplified form of the above polynomial. From this we have to multiply this bracket with this bracket, and we have to compare the coefficient. We have to compare the coefficient of z raised to minus 2n, z raised to minus 2n plus 1. Likewise, first compare the coefficient of z raised to minus 2n. For this we have to multiply this a0 into z raised to minus n with an of z raised to minus n. Once we have to multiply these two terms, here you can see a0 into z raised to minus n into a of n into z raised to minus n. This becomes as a0 an, and this becomes as z raised to n minus n bracket square, and this becomes as z raised to minus 2n. And this is the two terms contributing to the z raised to minus 2n, means coefficient of z raised to minus 2n becomes as a0 into an. Now collect the terms which are coefficient of z raised to minus 2n plus 1. For this, the first term is a1 into z raised to minus n plus 1, that is this term a1 into z raised to minus n plus 1, and we have to multiply this term with the an into z raised to minus n. Here you can see we have to multiply these two terms. It becomes as a1 into an. We have just split this z raised to minus n term into z raised to minus n into z of 1 into z raised to minus n. We come at the conclusion that this becomes as a1 into an z raised to minus 2n plus 1. As this becomes z raised to minus n into z raised to minus n becomes z raised to minus n bracket square. This becomes as z raised to minus 2n, and this z raised to 1, due to this z raised to 1, here you can get minus 2n plus 1. And the second term we have to multiply is a0 into z raised to minus n, that is this term, to the terms with a of n minus 1 z raised to minus n plus 1. With this multiplication we get the results, that is a0 into a of n minus 1 into z raised to minus 2n plus 1. As we see previously here, from this we have to split this z polynomial, and from this we get the results that z raised to minus 2n plus 1. These two terms contributing to the coefficient of z raised to minus 2n plus 1. Therefore, the coefficient of z raised to minus 2n plus 1 can be written as this a1 into an, that is this, and a0 into a of n minus 1, that is this. Now here you can see we can obtain the coefficient of power of z raised to minus 2n into and z raised to minus 2n plus 1 as it is, as we can see previously. Here one correction there is in the books, that is it should be a0 into a of n. Here it is taken as a of 1. This is wrong. You have to further check. Likewise, we can write the coefficient for all the polynomials into z raised to power. We can write the further coefficient for all polynomial. From this two multiplication, we come at one result, that the coefficient of z raised to minus I is equals to the coefficient of z raised to minus 2n plus I. that is we can see here the coefficient of z raised to minus 2n is equals to a0 into an, but at the same time the coefficient of z0 is also same as a0 into an. Likewise the coefficient of z raised to minus 1 is equals to a0 into a of n minus 1 plus a1 into an. This coefficient is same as coefficient of z raised to minus 2n plus I, 2n plus 1. That is, here say that the coefficient of z raised to minus I is equals to the coefficient of z raised to minus 2n plus I. From this here suppose we put I is equals to 0, means z raised to I means here we put 0, means this z raised to 0 coefficient must be equal to the z raised to minus 2n. Here I value is nothing but 1. Here we can see that z raised to minus 1 terms coefficient is same as z raised to minus 2n plus 1. The coefficients are same, therefore we can say the polynomial is self-reciprocal. From this we can say that a of z inverse into a of z inverse is in the form of alpha 0 into z raised to minus 2n plus alpha 1 into z raised to minus 2n up to a of n minus 1 z raised to minus n minus 1 plus alpha n into z raised to minus n, likewise continue up to alpha 0. From this we can say that our polynomial is self-reciprocal and it is symmetrical about z raised to minus n. Why this is symmetrical about z raised to minus n? Because we say we consider that our polynomial is of degree n, therefore we say that our the polynomial a is symmetrical about z raised to minus n. What is mean by symmetric? That is from this you can see that here we take reference here. From this the coefficient of z raised to minus n plus 1, that is alpha n minus 1 is same as here come here, that is this coefficient is same as this coefficient, and at the same time the coefficient of z raised to minus 1 is same as the coefficient of z raised to minus 2n plus 1. That is the coefficient of z raised to minus I is equals to coefficient of z raised to minus 2n plus I. From this we can here conclude that the coefficient which is coming here, this same coefficient is coming here, means the polynomial is symmetric about some reference, that is the reference is taken at z raised to minus n. Now suppose due to this symmetric coefficient we said that the polynomial which is taken, that is a polynomial, is self-reciprocal. Now take another polynomial in the degree of z inverse, that is b of z inverse is the another polynomial with degree of db, and the degree of db is nothing but degree of a minus k, which is equals to n minus k, because degree of a is nothing but n. This k is taken, we assume that there is some delay in this b polynomial as compared to the a polynomial, therefore we taken it as a k, that is n minus k for delay. From the logic of a polynomial we also say that b polynomial, that is b of z raised to minus 1 into br of z raised to minus 1 will be self-reciprocal polynomial with the coefficient symmetric about z raised to minus n plus k. Here b of r is nothing but the reverse polynomial for this b polynomial. Here we taken z raised to minus n plus k, because we have already proved that that is here our a polynomial is a reciprocal and it is symmetric about z raised to minus n due to the delay of k unit. Due to the delay of k unit, the b polynomial is symmetric about z raised to minus n plus k, and at the same time if we suppose that if you consider instead of b of z raised to minus 1 into br of z inverse, we have taken it as a z raised to minus k into b into reverse polynomial br, we have taken in this form the polynomial, then we can say that this polynomial is self-reciprocal polynomial with coefficient symmetric about z raised to minus n. From this conclusion we can say that the polynomial that is a of z raised to minus 1 ar of z raised to minus 1 plus z raised to minus k into b of z raised to minus 1 into br of z raised to minus 1 is a self-reciprocal. That is, we have proved this separate term as a self-reciprocal, and this term separately as self-reciprocal, and we come to the conclusion that this whole terms is a self-reciprocal. Here this is the all process in spectral factorization.